Now we got this Cartesian coordinate. Okay, Cartesian coordinate, which is 2D axis in plane, and then we got a 3D axis in space. Okay, so 2D we see y, x, which are 2. 3D we see z, y, x in space. So you see the difference. When we work in plane, we see a 2D, and then when you work in space, we see a 3D. Okay? For conversion of 2D from Cartesian to polar, this is how you get your resultant. You take the point that you have, which is if it was a square here, ax, and y, ay here. So those 2 points, which is maybe 2, maybe if this one was 2 and that one is 3, so it will be 2 square, 2 to the power of 2, 3 to the power of 2, and 2 to the power of 2. So you take their square root. So that will be your resultant. And then the resultant, it will be the point that we have in between. That's what we call the resultant. And then you take the magnitude. When you put like this magnitude. Now for 3D, I think this one is still we're still working with 2D. We haven't started with 3D. From polar to Cartesian, this is what you're going to use to go back to the Cartesian form. This is the formula you can use. This is a 2D because we only have x, y. So to go back to that form, and then the angle is actually what you see in between there. Alright, let's see more. Now when we go for cylindrical, we see 3D. Okay, you can see z, y, x, and then this is a representation of the point R, the angle, and this should be phi. Okay, so this is what you see for 3D. Okay, it's actually, let's just leave it aside, it's one. So this is like a cylindrical coordinate. And this way you're going to find theta. So from 0, and then we could have something like this, like a cylindrical shape, and that point. This is how you can represent them. And then we got polar coordinate, which is constituted with R and O. This is a polar. And then you can see we can get x and y from this. This is a 2D. This one is a 2D. That one is a 3D. You can see the representation. The Cartesian coordinates, since we have A, B, C, D, C, so this is a 3D. Normally this should be AX, AY, AZ. So you could find those points there, for example. Okay, something like that. Now, let's see the conversion. Convert from cylindrical to Cartesian. Okay, we're going to convert from cylindrical to Cartesian. So what is gonna be x equal to the radius cos O, y equal to sine O. This is like the conversion that you can get. So for you to get the value of x and y and z equal to z, this is the conversion from cylindrical to Cartesian. Okay. Now we're not done yet. Now conversion from Cartesian to cylindrical, you get the resultant from x squared y squared, and this is when you work with plus this is you can use it for 3D. Okay, so this is how you can solve for those unknowns, z equal to z, and the same goes for this. This is when you work with 3D. You can see we have z. Okay, let's go to this spherical coordinate system. This is a representation of spherical Okay, you can get the radius, the angle, and then that symbol is a 3D space. So you can see we have three terms, so distance and angle. And then the conversion from spherical to Cartesian, this is what you see. So we get x, y, z in 3D. And then angle, and those points that you see inside there. You can, this is how you do conversion from spherical to Cartesian. Alright, let's see more. Now convert from Cartesian to spherical coordinate. This is Cartesian, and then we're going for a 3D conversion, and then this is a spherical conversion that you see here. Okay, so this is how we do it. So we move from Cartesian to spherical coordinate.